Hi guys, welcome to the optional video for the second computer lab session. In this video, we are going to cover some common Boolean functions that are Boolean for the well-known distribution in R that follow the same pattern of naming conventions, which start with the first letter as D, P, Q, R, and each of them stand for a unique function. Say D is going to the function that start with D will compute the density. The function that start with P is going to compute the distribution function, which if by default you set the lower dot tail equals to true, it's going to get you the CDF as the and if you set the lower dot tail equals to false, you get the probability of x greater than the threshold instead, which is the survival functions. And Q stand for the quantile function, and R stand for function that generate the random variables from the distributions, and then comes with the name of the distribution, which T stand for T distribution, norm for normal distribution, POIS stand for Poisson distribution, and there are many other distributions as well, available as well, but I'm not going to cover one by one. And we're going to mainly focus on the functions that start with P and Q only, because this is for the hypothesis testing. You're going to need the qnorm function if you're using the you're going to use the function start with Q if you're using the critical failure approach, and you're going to use P function somehow to get the P value, regardless for left tail or right tail. Like maybe there will be slightly different argument setting, but yeah. Let's start with the function start with D. So it's going to compute the density, and we will use standard normal as like if you check the out documentation for the density, like qnorm, say, we can see that like by default it means is equal to 0 and SD equals to 1, so it's a standard normal distribution unless you specify another value, so mean or standard deviation. And the first argument you're going to provide is the quantile. So let's use a well-known quantile for a standard normal distribution, say 97.5 percentile for standard normal distribution is 1.96, right? So we can easily calculate the density function, and then if we integrate over this density function from the negative infinity to positive to this threshold, we'll get 97.5%, which is which I will not cover it, like it's probably is very well known. So now let's move on to the function start with the probability function that start with P. It's going to calculate the cumulative probability density, which is the CDF for us if we just let the lower dot tail equals to true by default. So we do not, if you want to use the default, you don't have to specify lower dot tail equals to true. So if we get pnorm, it's roughly 97.5%, right? So, and similarly for PT should get a similar result, like if we, like you can see that with a large enough degree of freedom, is roughly the same as the standard normal distributions. And on the other hand, if you want to get the probability of the random variable that exceed a certain threshold or critical value, there are two options. One, you can use 1 minus the CDF, which will give you like roughly around 2.5%, and the alternative, like you can calculate the shaded area in the right tail, which is this part, by setting the lower dot tail equals to false. And if we, you can see that it's actually giving you the same result. Maybe there will be floating point rounding issues, but it should be roughly the same using the lower dot tail equals to false. And you can also compute the you can also get the quantile or critical value from functions start with q. So for instance, if you want to get the quantile of the 97.5% for standard normal distribution, so we can just say qnorm equals 0.95, and we can see that it's very close to 1.65. And similarly, for if we want to get the quantile for a t distribution, say like like for 95% distribution, like the first argument for the function start with q is p, which is the probability. So we will also say 95, and then the degree of freedom maybe 100. Like if we follow the computer lab exercise, 196, right? So we can see that like the critical value that generate from student t distribution and standard normal distribution is quite similar when the degree of freedom is large enough. The last one is to use the R function to randomly generate some random variables from the distribution. So we can say like for instance, we would like, let's try a different distribution, say binomial distribution, and we are going to provide the we're going to generate maybe 10. You can see that, and the first argument is how many random variable you would like to generate, or how many observations. I would like to generate 10 observations, and size is going to number of trials. So I would like to Bernoulli distribution instead, like, and then the success rate, the probability is the success rate maybe like setting is equal to 0.3. So each time I run, you will generate a 10 random variable from the Bernoulli distribution that with the success probability of 0.3. So yeah, basically that's the optional video for the distributions.